Hey guys, we're going to talk about chapter 16 today in our textbook, which it's a good idea to have read that before you begin the lecture notes. It's about gases, liquids, and solids. Okay, so first off, we have to remind ourselves of what we already know about gases, liquids, and solids. So obviously this is ice, that's a solid, this is liquid, and this is water as a gas. And then the fourth state of matter that we don't talk very much about, but that does exist, is called plasma. It's basically like, fluorescent lights or neon lights that you've seen for open signs and everything like that. Okay, and so from 111, what we remember is that solids and liquids are not compressible. If you have a syringe at home, no needle, just the syringe part, like you might use for dosing children with medicine. You can suck up some water and put your thumb over the bottom so it doesn't squirt out and try to compress it. And what you'll find is that it doesn't change the volume at all. You cannot compress it. You can't squish a liquid. You can do the same thing by sucking up some air and putting your thumb over the end and squishing that, and you can easily compress a gas. So we think about gases as being the only state of matter that's compressible, meaning I can squish it. Gases and liquids both don't have an individual shape. They like to take on the shape of the container. Gases have an unlimited volume, or not a fixed volume, and liquids have a fixed volume. So in other words, if I spill a liquid on the floor, it's only going to occupy a certain amount of space. It's not going to spread out all over the room, whereas a gas definitely would. Okay, so that's just a reminder from 111 of what we already know. All right, so on this slide, we're looking at different phenomenon that happen because of the properties of solids, liquids, and gases. So liquids have surface tension, which means that the liquids stick to each other. They have the molecules have a tendency to want to be close together. So when you try to pour a liquid, it kind of forms like a droplet instead of just immediately dispersing throughout the area. That is because of surface tension. So this little bug in the picture here can walk on the water because water has really high surface tension. If you look at this picture here, the atom inside of the water sample, like in the middle of the sample down here, has other water molecules interacting with it pretty closely, but in a balanced way, so they're kind of symmetric. The ones on the top don't have anything pushing or pulling on them, so that means that the interactions on the bottom side are very strong. There's nothing kind of counteracting it on the top. So that creates kind of like a network of really strong attractions along the surface of water. That gives water a really high surface tension. So when you have attractive forces keeping things together, they fall into the category of intermolecular forces. And in the case of water, it's hydrogen bonding. Another example is dipole-dipole interactions. We'll go into the details of what that means in a minute, but basically you have attractions between the two particles. That means they want to stay close together. It's the same reason in the last lab that when we have this figure of temperature change versus heat, these flat parts where the phase is changing requires energy to be putting into it if you're going from, say, a solid to a liquid, because energy has to be put into that because you have to separate the particles and they're attracted to each other, so you've got to put a little bit of energy in to get them separate. All right, so what I want you to do is watch this video by NASA and make a little note about anything that surprised you or was impressive or interesting or any questions you have here about that video. You can get to this video just by opening up the lecture slides and then going into presentation mode and clicking on the link or copying it directly from the slides. All right, so this is actually 16.2. We changed the chapter numbers a little bit. 16.2 is about the various different physical properties that liquids have. All right, and we've observed these sometimes at home or in the lab. Here on the first picture we have a meniscus. So this kind of reflection looking thing on the surface of water is caused by the molecules at the edge of the glass tube are attracted to the glass. So they just kind of climb up the edge of the glass, and it creates this kind of edges where the things close to the glass can travel a little higher than the pieces of water that are in the middle. So you get this meniscus that's kind of shaped like a U. Not all things are attracted to glass, though. Many substances are they're repelled by glass. So here's an example. This is mercury, and mercury is definitely repelled by glass. So what you have is a meniscus that goes the other way. It goes up like an upside down U or a frown. And that happens because the particles of mercury are afraid, or like phobic, of the glass. So they run away, and that means they kind of cluster together in the center of the tube instead of being closer to the glass. So meniscus is caused by an attraction or a repulsion between the container and the liquid. Okay? When there's an attraction, you get capillary action. So plants use capillary action to move water and nutrients from its roots all the way up to the leaves at the top. And so what's interesting about this is that plants, of course, don't have muscles, so they have to do this using like passive mechanisms. And so one of the main ways of getting water to the leaves is by capillary action. And so a plant that's short has really big capillaries like this. A plant that's tall has to have really, really thin capillaries, because it means that the interaction between the glass and the water is bigger. You have more surface area for them to touch each other with by squishing the water column. So that means that the skinnier the capillary, the skinnier the glass tube, the higher up the column travels. If you've never seen this before, it is an excellent example of capillary action. You can take celery or carnations that are white or whatever kind of flower that's white, and you can put it into water that has food coloring in it, and it'll absorb the water and the food coloring. So like this yellow water gets shown in the leaves of the celery, and the red one shows up like that. Stores use this quite a lot. They produce purple flowers and blue flowers and things that are hard to do in nature by dyeing the water that they feed to it for a few days before you buy it. But that's all from capillary action. You can actually make, I've seen on Pinterest, you can make carnations and roses that are like tie-dyed by splitting the stem lengthwise and then putting one end into, say, a red color and the other one into a purple dye, and then they sort of mix the colors together in the petals. So it's pretty cool. So you can try that at home if you want. Okay, another physical property of liquids is something that we call boiling point. So boiling point is the phase when you're going from a condensed liquid into gas particles like this. And so basically what you're doing is you're putting a lot of energy into it, so a lot of heat to do this. And the reason for that is that you have to separate the particles. So you have to break up those strong attractive forces between particles. When they say point, what they mean is temperature. So boiling point is the temperature at which something goes from a liquid to a gas. So of course melting is kind of similar, right? You're going from a solid, You're going from a solid something, say maybe ice, whatever it is. These are my solid particles. To a liquid. Okay, so a solid is the most condensed phase of matter, and a liquid is the next most condensed. So we still have to put in heat to do this because you're still separating the particles. And of course, this is going to happen at a particular temperature for any given substance. So at which the solid goes to the liquid phase. For water, the temperature at which it goes from solid to liquid is, of course, 0 degrees Celsius, or 32 Fahrenheit. And for the boiling point, water boils at 100 degrees Celsius and 212 Fahrenheit. Okay, so that's just for water. Everything has its own boiling point, though. And the higher the boiling point is, the stronger those intermolecular forces have to be. So as boiling point goes up, that means that the IMF, the strength of the IMF, is higher. So comparing, say, water to something else like ethanol. So ethanol has a chemical formula of CH3CH2OH, and it has a boiling point of around 79 degrees Celsius. That tells me, when I compare the boiling points, it tells me that ethanol has weaker IMF because its boiling point is lower than water. Okay? So even if I don't know the structure, I can use the boiling point to help me figure out some characteristics about the molecular structure. Okay. So now, we have boiling point, we have melting point. Another important vocab word is evaporation, and we know this one because you've observed this happening. If you spill water on the counter and don't wipe it up, eventually that liquid water will evaporate, right? And the same thing happens if you ever leave a pot of water on the stove. It all evaporates out. It just disappears. Even if there's no heat, the molecules will slowly leave the container. However, if I put a lid on it, what happens is that the water molecules can't escape anymore. And eventually they're going to kind of like bounce all around in this container, and eventually they end up going back into the liquid phase. Equilibrium is the state that describes the process where some random water molecule goes from liquid to gas, and some other one at the same time has to go the other way from gas to liquid. That process is called equilibrium. Now, I want you to think about this question. If I heat up the water in this flask in C, would that cause the rate of evaporation to increase or to decrease? And why? Okay, so take a second and jot that down in your notes. Okay, so if you open the slides in presentation mode, or if you click on this link, you can see that these images here are actually animated. Okay, so we can see a simulation for what's happening on the particle level, and that helps us to visualize vapor pressure. This picture, let me turn that into something that's not red. This picture here is a liquid forming a gas, and this one is a solid that's forming a gas. And the gas particles are separated and kind of zooming all over the place, so that's how I can tell those apart from the other condensed phases. Vapor pressure is a measurement of effectively how many molecules are in the gas phase and how fast they're moving. So it gives us a way of figuring out if a particular particle is really good at escaping the surface. So if we have a high vapor pressure, so if vapor pressure is really high, so if I'm comparing two things, it would be an increased vapor pressure, then that tells me the intermolecular forces must be very weak. Okay, so intermolecular forces are what keep things in the liquid phase down here. So if they had strong forces, they would prefer to stay together. They would prefer to stay a liquid or a solid. All right, but some things do not have strong IMF, okay? And when that happens, more of their particles are able to escape into the gas phase. So that means, more particles. That means the vapor pressure increases. If you have more gas particles, then vapor pressure is high, okay? All right, we can measure this. So if I take this apparatus in figure A, where I have some liquid ethanol, which is alcohol, like, vodka or something. I take this and I have a sealed container. So these valves are closed. But on the other side of the valve is a column of mercury in a U tube. Not the website. It's just a U-shaped tube. Here, when we heat up, or rather, when we, we're not heating yet. When we open this valve so that the gas vapor coming off of the ethanol can kind of bounce around down this tube until it gets to here, what happens is they push on this column and move it up. And the distance that they move it up by is the vapor pressure. So you can think of vapor pressure as literally how much force gas molecules can sort of use to push on a column of mercury.